So this section is all about the reciprocal functions, cosecant, which is essentially just 1 over sine, secant, which is 1 over cosine, and cotangent, which is 1 over tangent. Um, I actually don't like this section in terms of studying it. Your best way to study it is to pull up a sine curve and then make a 1 over sign to understand the connection. 1 over sine takes all these values here and puts them 1 over. Let's make it just to the right. So smaller equal to x equal to 2 pi. We'll do that, and we'll do the same for this one. We'll just show 1. As a number goes between 0 and 1, for instance, when you do 1 over 0.57, you create a number above 1. Any number divided by a decimal below 1 creates a number bigger. And the smaller this decimal, the bigger that number becomes huge. Which is why as we approach like very small values here, let me put it over f of x. If I take an f of 0.101, very small value of x, I discover an incredibly small value of y. That's as we get very close to 0 here. Which means if I take this number and put 1 over it, for the same value of x, we're going to have an incredibly high value of y up here on the 1 over sine curve. Keep in mind that 1 over sine is the same as cosecant. Let me just put this over. It's the same thing. Notice that the one value they share is that y is equal to 1. That's because 1 over 1, when you take this 1 and you divide it by 1, or take 1 over 1, will still be 1. So this is the only value they share. And as the y values become less than 1 here, we get huge values of y for this one. The x values are shared. The x values are shared. And it's y over here goes down is because these are negative numbers. So 1 over a negative value over here will produce an incredibly high value. And of course, as your sine curve approaches 1, the cosecant curve approaches 1, and they both meet at 1 and then separate again. Also notice that cosecant has a asymptote at 0 degrees. X is equal to 0. It has an asymptote at x is equal to pi. And it has an asymptote at x is equal to 2 pi. And that is because on the sine curve, those are the values of y that are 0. And 1 over 0 cannot exist. 1 over 0 cannot exist. So you have an asymptote for the cosecant curve. The same is going to be true for the cosine curve when we switch to cos here. Just the asymptotes are going to be 90 degrees out because the cosecant is 90 degrees out. There's a cos curve. Here's 1 over cos. And let's just get rid of this. There we go. And here is the secant, which is the same thing. Notice that it's this one, when I take one period, we're kind of missing half of our cosecant. They exist in the negative realm in the next period. But if we're just looking at one period, that's what they are. And it's the same logic. 1 over a decimal will create a large number. In this case, the tangents are at, or why is my brain? Doesn't matter why my brain is freezing. They're going to exist at 3 pi over 2 and pi over 2. And so that's where you cannot have 1 over 0, because that's where the cosecant has a value, y value of 0. 1 over 0 will create a non-existent number, which is why you have vertical asymptotes. That's the word I was looking for. Vertical asymptotes there. Notice, you might ask, and this is more cool, and now here's a tan curve. The tan curve has already got asymptotes, where since it's sine over cos, where cos is 0, you cannot have. So let's look at how it relates to cos. Since tan is sine over cos, you can see that they exist wherever the cos curve hits 0, you have a vertical asymptote. So that's why the tan curve has vertical asymptotes at the same spot where cos x is 0. Notice for that the cotan curve is going to look a lot like a tan curve, except it's flipped. See, if I flip it, all right, let's see if it works when I put it in brackets. There we go. And then put it out of phase by pi over 2. So that's a cot curve. It's simply flipped along the y-axis and out of phase by pi over 2. Otherwise, a cot curve kind of looks very similar to a tan curve, except that its vertical asymptotes will be where sine x is 0. So its vertical asymptotes, let's just get rid of this one. Its vertical asymptotes will exist when sine has a y value of 0, because a cotangent is cos over sine. Let's discuss very quickly a more important subject. Why is cos curve 90 degrees out of phase of a sine curve? Let's, for that, look at any right angle triangle and look at the basics of SOHCAHTOA. We're going to talk about this angle x and this angle O. Let's talk about this angle x, and let's look at its sine value, sine x. Well, the sine x of any value is opposite over hypotenuse. And in this case, just to make things easier, we're going to make the hypotenuse 1. Well, if sine x is opposite over hypotenuse, and the hypotenuse of 1, sine x is simply the opposite. So in this case, we're going to call the opposite side over here side A. And they usually use small letters, small side A. Now let's look at the cos curve, or the cos value, using SOHCAHTOA, of cos circle. Circle cos value is adjacent over hypotenuse, but we've already determined we're using a hypotenuse of 1. Therefore, cos of O is equal to the adjacent. Well, it looks like the cos of adjacent is also sine 1. Also sine 1. So sine x is side A, and cos O is also side A. That is because if we look at the degrees here, if 90 degrees here is used up, these two must add up to 90. These two must add up to 90. O plus x must equal 90, which means cos and sine will always share the opposite degrees. For instance, sine of 30 will be equal to cos of 60. Sine of anything, 12, will be equal to the cos of 90 minus 12. What's 90 minus 12? 78. You can check this out in your calculator, but it means that sine and cos will always share this relationship of being 90 degrees out of phase, because they share a 90 degree right angle triangle, and they'll share the 90 degrees that is left. And you might say, well, why does that make everything out of phase by 90? If you look at this, we're really 90 degrees out of phase in a circle. If I add 90 degrees to 30 degrees, it's 120. But 120 is the same as the acute angle 60, which is the same as cos 60. So it means if I were to add 90 degrees to any sine value, I'm going to get well, that's probably not quite accurate, but you can see that if I add 90, suddenly I enter into different territory. And it's solely because these two angles here that are left over share the left over 90 degrees. And that is why a sine curve is simply a cos curve that's out of sync by 90 degrees. They're out of sync by 90 degrees. More on that later. Let's do these questions. Now, one of these questions I'm not going to do because I actually think it's detrimental. This is turning it into an arithmetic sequence. An arithmetic sequence is separated by a constant difference, starting with the first value, a, and you take whatever term you're working with next, you subtract 1 and you multiply by the difference. They're trying to show a connection between cosecant x and an arithmetic value. I don't think this is suitable to think about, because that's true of any repeating curve. I can turn sine x into an arithmetic value in which every time the difference is 2 pi, because as I go up, the next one's 4 pi, As I go up, the next one's 6 pi, but it's the sine curve repeating over and over again, which means I can take any value of sine and add 2 pi, and I will have the next value, like this. So in this case, sine of 30 will give me the same value as, I don't know why I gave, oh, it's because I've got to do pi over 6. Will give me the same value as sine pi over 6 plus 2 pi. The arithmetic difference this time is 2 pi. I don't even have to add them, but if I were, it'd be 12 pi over 6, which is the same as 13 pi over 6, will give me the same value. And over again, if I keep adding 2 pi, I will get the same value, no matter how many 2 pi's I add. This is simply an arithmetic sequence where the difference is 2 pi. And the starting point is whatever starting point you choose. We could use it as 0, 0. So the next point will be 2 pi 0. And the next point will be 4 pi 0. And the next point will be 6 pi 0. Simply by adding an arithmetic difference of 2 pi. But all these curves are like that because they all repeat in the same fashion. They all repeat in the same fashion. There's no real need to focus on cosecant as an arithmetic difference. And I really think it's deterring from trigonometry when we do so. This is a fair enough examination, but we kind of did it. They want to know the location of each of the following. So if we look at secant, secant is the opposite of cosine. So let's start by graphing, not the opposite, the reciprocal. Let's start by graphing the values of cosine, just to understand it. It's going to go down like a bird, and then up, and then down. And let's look at the values where cosecant is 0. Cosine, this is a cosine curve, rather, where cosine is 0. Well, it's 0 at pi, 2, 0. And it's 0 at 3 pi over 2, 0. Which means, since that y value is 0, if I were to take 1 over 0, I get an impossible value, which means for secant, which is secant is 1 over cosine, that is where I will find the asymptotes. And they will repeat the difference between there is every pi. So every pi will get that. Where n is equal to any value and x is in radians. So we're going to have a vertical asymptote at x is equal to pi over 2 plus any value, every value, like I pi if you want, onwards. You'll find vertical asymptotes, and it's even plus and minus. You will find vertical asymptotes backwards every pi, multiplied by whatever value we're repeating in forever and ever. You will find those asymptotes. Where will you find the max values? The max values are interesting because you will not find the max value. As these get less than 1, but close to 0, the curve of the cosecant goes way up. And there is no real max value because there is no real number down here that can exist. Now, if they mean I is an integer, that's difficult to say because almost every value of x is a fraction. But if we're just looking at where the maxims occur, they occur slightly to the left of the asymptote and slightly to the right of the asymptote, as close to the asymptote as you can get. The min values will occur right here when sine is at 1 and minus 1. So here, here, and here, which means the curve of the cos will touch that 1 and share that 1 with the cosine, which means we're talking 0, 1, pi, minus 1, and 2 pi, 1. That is where you will share. And then it repeats, as you can see, every pi forever. So do the max values. They repeat every pi forever right near the asymptotes. There's no real way to describe where the maximums occur. Find an expression that describes the location of each of the following for cotangent. Vertical asymptotes. x-intercepts? Well, cotangent, I should copy that question. Well, essentially it's cotangent. They want to know the vertical asymptotes and the x-intercepts. If you look at cotangent, cotangent is going to be the same as sine. Tangent is sine over cosine. So cotangent is going to be cosine over sine. The only time we're going to have a vertical asymptote is when this value is 0. So we need to find when sine of whatever is 0. Draw a sine curve. Here's the 3 spots where sine is 0. Therefore, that will be the vertical asymptotes for cotangent. So it's going to occur at x is equal to 0, x is equal to pi, and x is equal to 2 pi, repeating forever every pi. So for cotangent, the vertical asymptotes are 0 plus any value times pi, plus or minus forever. So they're going to occur at pi, 2 pi, 3 pi. You just keep adding whatever this means. It just means 1 more, 2 more. I think they use k often. So it's 1 more, 2 more, 3 more, and the left direction as well. You'll find asymptotes forever. Now, the next question says, what about x-intercepts? X-intercepts are going to be when cos is 0. Why? Because we have 0 up here over a value of sine that's not 0. So we have to look at where cos is 0. Let's do that. If we look at cos, it comes down like a bird, goes back up. Here's where it's 0. That is where pi, that is at pi over 2 and 3 pi over 2. So at those two values, and repeating every pi, notice pi over 2 plus pi is 3 pi over 2, and it will occur over here and over here and back here and back here. So it's pi over 2 plus or minus a k value, which is a whole number, times pi. So it just goes on forever. And that is where you will see the cotangent come down and touch that. And just to prove it, you can always pull up a cotangent curve. And show it x is equal to pi over 2. And let's see if it'll, there we go. That is where the tangent's 0. And then every pi later. Forever and ever. And then, of course, the asymptotes are exactly what we said. X is 0, x is equal to 0, and every pi later. And every pi before. So it's very easy to figure out where those exist by knowing what the relationship is to cos and sine. That was 3. 4, using graph technology to graph that. Well, I'll leave that to you. Where do they intersect and why? Compare these values with where sine x and cos x intersect. Well, that's fair enough. So we're going to see the relationship of where sine, and it should be at 45 degrees because that's the only values that sine and x, cosine and cosine share, and every 90 degrees later. So if we look at cos x and sec x, we can see that they share right here, pi over 4, which is 45 degrees. 45 degrees later, 2 pi later, 2 pi later, every 2 pi. Let's look now at where cos and sine share. They share at the same values, pi over 4, and every 2 pi later, pi over 4. They also share a negative value, I should point out, which is the equivalent of negative pi over 4, but in quadrant 3. Because that's when both cos and sine can be negative, quadrant 3. In every other quadrant, sine is either positive when cos is negative, or cos is positive when sine is negative. But here in quadrant 1 is the only time they're both positive, and here in quadrant 3 is the only time they're both negative, which means, again, that's something I should have examined on the other ones. That will be true for the cosecant and secant graphs. They will share point here and a point here. See the negative, that's quadrant 3. Pi, that's 45 degrees obtuse angle. acute angle rather. But that's in quadrant 3 where it's 180 plus 40, it's 225 degrees. And every 2 pi later for that one as well. So this is the only area where both cos and sine are negative, and this is the only area where cos and sine are positive, and it's also the only area where secant and cosecant are positive, and both negative, sharing the same value. They will share the same numerical value of 45 degrees, but opposite signs in the other two quadrants. All right, are congruent, okay, related by translation of pi over 2. Yeah, this just goes into where showing that sine, any sine graph put out of phase by half of its period will equal the cos phase. Is this relationship true for cos x and secant x? Yes, of course it does, because they're essentially the same thing. So if I add pi over 2 to this, I'm going to overlap. Or sorry, if I subtract, it's got to be a subtraction. They will overlap. See? They overlap. So it's out of phase. If I add pi over 2 or subtract, shift it to the left pi over 2, they don't. They pretty much end up mirroring each other. So why is it opposite? Because they're reciprocal. So it's minus pi over 2 instead of plus pi over 2. Two successive transformations can be applied to the graph y is equal to tan to cotan the graph. Cotan. There's more than one way to do this. Okay, yeah, of course. There's always more than one way to transform a graph into the other one. This, again, is easier using graphing technology. Let's take tan x, and I think I did it for you once already. It's a reflection in the x-axis. We're going to take cotangent x. So notice they're waving different directions. So to make them wave the same direction, I have to reflect it in the x-axis. Boom, right there. That was enough to make it wave the same way. Now I just got to put them pi out of 2 differently. And actually this minus 1 should be out here. So therefore, it's a reflection in the y-axis and put out of phase by pi over 2. Let's see if going the other way will work. So that's one way. Oh, look at that. The other way works as well. So that's a phase pi over 2 to the right, horizontally to the right. Okay, fair enough. Let's leave that and see if there's ways of making any phase as well. I mean, you could add 3 pi over 2 and you'll get the same thing. You could keep adding 5 pi over 2, you get the same thing. So you can multiple variations of 2 pi or subtract. Same thing. Interesting, the only way to make them match those reflecting in the x-axis or y-axis. Let's see what happens if I reflect it in the x. Oh, no, now. So by turning it upside down, reflecting in the x-axis, I've done the same. And let's just make this pi over 2. So it doesn't really matter which way you reflect it because it'll get the curve going the same way. So you can do a reflection in the x or the y to get them to match and then simply put them out of phase one way or the other by pi over 2. And there's endless ways to do it. Use transformations to sketch the graph of each function. Yeah. I mean, really? You'll have to take, I suggest you do it, but it's the same thing. So this x is being multiplied by half, which means you take all your x values of cotangent and multiply them by 2. And all the y's stay the same. This x values you multiply all by a half, and then you subtract pi over 2. This one has a y transformation 1 down, so you simply take all the y values and subtract 1. This one is not factored correctly. You got to factor out the 0.5, and you get x plus pi over 2. No, x plus 2 pi, which means you got to multiply everything by a half, all your x values by 2, and then subtract 2 pi. I'll let you factor that out to make sure that's right. And there's the 6.5. I don't like those questions. Really just take Desmos and play around with the graphs to understand how they relate.